Chapter 8 Notes and Background Information. Every right triangle has a right angle, and coming from each of the right angles, we have what we call the legs of the right triangle. So this right triangle has two legs, and I'm going to label these legs leg A and B. And also, every right triangle has a segment that we call the hypotenuse. The hypotenuse will always be the longest leg in a right triangle, and it's always directly across from the right angle. And I'm going to label the hypotenuse C. The Pythagorean theorem states that if you have a right triangle, it is true that the sum of the squares of the legs, so here's the sum I'm adding together, and the squares of the legs, a squared and b squared, will always equal the hypotenuse squared. So this allows us to solve for any one of these three lengths when two of them are known. That's the Pythagorean theorem. The next theorem that we dealt with in Chapter 8, I'm just going to state here now. I'm not going to prove it as we did in class, but it goes along these lines. When an altitude is drawn to the hypotenuse of a right triangle. Okay, digest that statement. We have a right triangle. Right? The big one is the right triangle that we're speaking of. And an altitude, meaning the height or the distance from this vertex to this side, the altitude drawn to the hypotenuse. When an altitude is drawn to the hypotenuse of a right triangle, it divides the hypotenuse into two different segments. And for convenience sake, I'm going to call this segment A and this segment B. So if I add these two up, right, I will get the length of the full hypotenuse. But this altitude is cutting the full hypotenuse into two pieces. When that happens, there are three statements that are true. And they relate to, I'll go ahead and call this X. I'll call this Y. And I'm going to call this altitude Z. And here are the three statements that we will talk about. The first one will be the altitude itself. This altitude is the geometric mean of the two segments. You can look up at the textbook again the definition of the geometric mean, but the way that I taught you in class, that I prefer for you to write the statement is along these lines. So I'm writing right now, Z is the geometric mean. Z is the geometric mean, and the segments that Z is the geometric mean of A and B, the two individual pieces, A and B. Okay, Z is the geometric mean of A and B. The other two statements involve the legs. We'll look at this leg first, the one labeled X. This leg, right, of my original right triangle is the geometric mean, so let's go ahead and write that. X is the geometric mean of two segments, and the segments X is the geometric mean of are the portion of the hypotenuse that's adjacent to X, so A, and the entire hypotenuse. In this case, I don't have a variable representing the whole thing, so I'm going to say it's A plus this piece B. A plus B. So this leg is the geometric mean of the portion of the hypotenuse that touches it and the entire hypotenuse. The third statement that's true is very much like the second one, and it relates to this other leg. This leg, it turns out, which is labeled Y, Y is the geometric mean of, and it's the exact same pattern right here, the portion of the hypotenuse that's adjacent to Y, so here we would have B, and the entire hypotenuse. So I'll go ahead and write the A plus B. Okay. Again, these three theorems, these are all based on similar triangles. It is the case that when an altitude is drawn to the hypotenuse of a right triangle, it subdivides this triangle into two new right triangles. And we demonstrated in class that all three of them, the smallest, the middle one, and the entire one, are similar to each other. And these are coming out just because of the similar triangles, and the ratio of corresponding parts are similar. All right, so that's the second item that we should know. The third item is that we'll talk about here are trigonometric ratios. And it's important to remember that these are always related to a particular angle. So I'm going to be speaking from the point of view of this angle. If I was speaking from this angle, it would be different. And it's always one of the two acute angles that we write these ratios from. And here's our definitions. In a right triangle, right, and from the point of view of one of the two acute angles, the sine ratio is defined as the opposite leg divided by the hypotenuse. Okay, so let's talk about what those words mean. From the point of view of this angle, this is the opposite leg. Of course, this is a leg, and this is the other leg, and this will always be referred to as my hypotenuse. But let's go ahead and label this. This is my opposite leg, and I'm just going to abbreviate that OPP for opposite leg. And I'm going to label this one the adjacent leg, and I'll abbreviate that ADJ. And up here I have my hypotenuse, HYP. So from the point of view of this angle, I have an opposite leg, I have an adjacent leg, and I have a hypotenuse. Okay, and here are my ratios. The sine ratio, and I'll just do these in black, the sine ratio, and let's give this a label so that we can talk about it. So we'll call this angle A. The sine of angle A is defined as the length of the opposite leg, OPP, opposite leg, divided by the hypotenuse, HYP. The cosine ratio, the cosine of angle A, is defined as the length of the adjacent leg, ADJ, divided by the hypotenuse, HYP. And the final one here is the tangent ratio, and the tangent of angle A is defined as the length of the opposite leg, OPP, divided by the length of the adjacent leg, ADJ. Okay, so these are my three trigonometric ratios, and we just need to know them. We'll be plugging in information that's given in a particular problem into these statements, and then we'll be solving for variables. But the next thing that we want to talk about is what is meant by a grade, G-R-A-D-E. So you'll see roads that will say that there's an 11% grade. Next 10 miles, 11% grade. What does that mean? When you see that term, remember your horizontal change, we're always going to label 100. And if you're told, for example, that you have a 13% grade, G-R-A-D-E, what that means is, in this right triangle, for every 100, let's say it's 100 yards, every 100 yards horizontally traveled, there's going to be a change in an elevation of 13 yards. So for each 100, there's a change of 13. And you may be asked, for example, to figure out what this particular angle is if you know that you have a 13% grade. And without solving it yet, because we're going to talk about inverse trig functions next, but without solving it, the equation I would write, if this, I'll call this angle B, I would say from the point of view of angle B, I have the opposite leg and the adjacent leg, so I'd be using my tangent ratio, and I would write that the tangent of angle B is equal to the opposite leg, 13 over 100. 13 over 100 is actually 0.13. So we can just write that 0.13, 13 over 100. So the tangent of angle B is 0.13. The question is, what's B? And we're going to talk about that on our next slide with inverse trig functions. That we know that this leg is 9 units long, and this leg here is 40 units long. And we're gonna be asked, what is the measure of angle, and I'll call this angle B. How many degrees does angle B have? Well, to answer that question, we're going to go ahead and begin by just writing down an equation that involves our trigonometric ratios. And from the point of angle B, we see that we have the opposite leg, and we see that we have the adjacent leg. So the equation I'm going to write is the tangent of angle B is equal to opposite leg divided by the adjacent leg, 40. What I need to do now is apply some function to both sides of this equation that will undo the tangent function. And it turns out that there is a function, it's called the inverse tangent function, and as long as angle B is an acute angle, and it definitely is acute here, you can be assured that when you take the inverse tangent, you're going to get just the angle itself. So again, on each side of this equation, I am now applying the inverse tangent function. When I apply the inverse tangent function to this side, I get just angle B. And then notationally, what does it look like on this side? If I apply the inverse tangent function here, it will look like this. This is the inverse tangent of what I had, which was 9 over 40. Okay, now it just remains to evaluate what this expression is. And on your calculator, you'll notice on the tangent key itself, there is right above it, there's this function's here, so you may need to use your second function. So if we hit shift inverse tangent, we want to do the inverse tangent of 9/40. And when I evaluate this on my calculator, I get that B is 12.68 degrees, rounded to the nearest hundredth of a degree. If you do not get this value, that means that your calculator is not set up to currently measure angles in degrees. It's in either radians or gradians. And if you stop by, I will show you again how you make sure your calculator is in degree mode and the answers you're getting are degrees.